try to go again, try to share screen again. I think the problem is that I only have a certain amount of smooth sailing / high quality thinking I can do in a day, and I've already used all of my. If that was high quality thinking, that might be a problem. I don't know. All right. When we want to measure the rate of a reaction, some of you have thought about this before. What you're going to do is measure the appearance of product, or you can actually measure the disappearance of starting material as a function of time. So first derivative of product concentration as a function of time, and then that's going to be related to some rate constant, and then we'll have a rate law expression that depends on the participants in the reaction. For example, and then the exponents tells you the order of the reaction in a particular component. So if A equals 1, little a equals 1, we would say this reaction is first order in A. And similarly with B, if little b were something, we would say it was first or second order in B. It's kind of rare for there to be reactions where three things come together at once. Such processes are called termolecular, and they are known, but there's not that many of them. I will say you can write a rate law expression that just but for reactions that have complicated mechanisms, it's possible that the observed rate law doesn't tell you how many molecules are involved in the rate determining step. If it's a single step reaction, then you can. For example, in the SN2 reaction, right, we observe that the rate equals some constant times the nucleophile concentration times the electrophile concentration. We say that the reaction is first order in nucleophile and first order in electrophile and second order overall. And because we know that this reaction happens in a single concerted step, we can use the fact that the reaction is second order overall to make the conclusion that the reaction is bimolecular. That is, there's two different molecules involved in the rate determining step. All right, so that's rate law. And we can write different rate laws and may do that a little bit later in the chapter for different types of mechanistic setups. But I want to introduce transition state theory because it's influenced how we think about reactions and how we assess the rates of reactions, the kinds of kinetic experiments that we do. And the chief proponent of transition state theory is Henry Eyring, who was a professor first at Princeton and then at the University of Utah, where he became dean. And he was nominated 3 times for the transition for his for a Nobel Prize in chemistry because of his transition state theory. It never happened. But nonetheless, he's recognized as a key chemist in our century. So that's kind of fun. What else about Henry Eyring? If you haven't read the book that was written by, I think, his grandson, it's called Mormon. It's either Mormon Chemist or Mormon Scientist. I can't remember. It's worth a good read. He's got a lot of interesting things in there. One of the things I learned was that Henry Eyring met his wife, Mildred Benyon, while they were both in Madison, Wisconsin. He took her on a canoe ride through Lake Mendota, which is still there, as lakes tend to be. But all right. So the basic idea, starting with the reaction that's A plus B goes to C, of course, you can write a rate law that would look something like this. But Professor Eyring made the connection that you could also represent And this is thinking about something going over a transition state to products, right? Starting materials, products, transition states. This is A plus B. At the transition state, he envisioned something like that called the activated complex. Or, the two things come together, bonds partially broken and formed, and then you've got the new product C. He said that while you could represent the rate as some rate constant times the concentration of A times the concentration of B, you could also envision some other kind of rate constant and the concentration of the activated complex, right? If you had more stuff in the activated complex, he envisioned the reaction would go quicker. And then the small rate constant would be related, the little k double dagger would be related to this idea that once you get to the transition state, all you need is a molecular vibration to push you over in the right direction. All right. So with that in mind, the chief postulate of transition state theory is that you can pretend, because it's not actually true, but you can pretend that the starting materials are actually in equilibrium with the transition state. And that should give you a little bit of heartburn. That should make you uncomfortable because the transition state is a maximum. And equilibrium constants are related to Boltzmann distributions, which require that molecules occupy wells on a potential energy surface where there's enough time for them to redistribute their energy throughout all of their translational and vibrational and rotational degrees of freedom. Nevertheless, Eyring postulated that if you wrote this sort of equilibrium constant between the starting materials and the activated complex, then you could substitute, you could find an expression for the activated complex that would look like this. Rate equals little k, which is the rate constant for the molecular vibration that pushes you over the transition state, and then big K double dagger, which is the equilibrium constant, times the concentration of A times the concentration of B. So what Eyring really was doing, if you compare what we've written here to the rate law we wrote up here, Eyring was saying that our typical idea of the rate constant has some contributing factors, right? And one of them is the vibration, molecular vibration that gets you over the transition state once you're there. And the other relates to how much of that transition state activated complex you have in the first place. So for little k double dagger, you can relate that to, this is the Greek letter nu, which is the frequency of a molecular vibration. And these are typically on the order of 10 to the minus 13 per second, or 10 to the minus 14 per second, something like that. So really fast. And then some what is called a transmission coefficient, and I wish your text had come up with different letters to use. This is the Greek letter kappa, drawn in a terrible way. Greek letter kappa is what's called a transmission coefficient, and this is related to the fact that that crossing the transition state is not 100% perfect, right? You get there, and sometimes depending on your precise geometry, that molecular vibration may not push you over the edge. And so kappa represents the percent of molecular vibrations that push you over the edge. For the most part, we're going to assume that it's near 1, but it'll be different for every reaction depending on the characteristics of the starting materials in the transition state. Then for the big equilibrium constant between starting materials and activated complex, he just used the okay, hold on. I'm waiting to figure out what the math is. He had to use, at this point, statistical mechanics to derive this. And I don't know anything about statistical mechanics, but Dr. Seavey does, so you can ask him. Because the activated complex is at a high point and not at a minimum, you can't assume a Boltzmann distribution, and so you have to do something else. So you can't use k equals the exponential of minus delta G over RT. It's a little bit more complicated than that. And what he derived is another little k, Boltzmann's constant, times temperature, divided by Planck's constant, times nu, again, that molecular vibration, that's a prefactor, times the number E raised to the minus G double dagger over RT, where this is the activation energy. That's the difference in free energy between starting materials and transition state. So that would be this energy. All right. So, and you might ask, why are we bothering to deconvolute the rate constant into so many contributors? And the idea is we want to separate out from the rate constant things that are universally true, like how long a molecular vibration lasts, and constants that never change, and temperature that you can change on a regular scale, versus something that depends on the reaction, which is the change in overall free energy. So now if we bring it all together, remember our rate constant, I'm going to rewrite the dumb rate law. We said rate constant K is equal to little k times big K. So you put that all together, nu kappa is little k double dagger, and then big K double dagger is Boltzmann constant times temperature, Planck's constant again times nu, then E raised to the minus delta G double dagger over RT. I'm not going to ask you to derive this on your test, so don't worry about it. Things make more sense to me when I do the algebra, unfortunately. So, yeah, your expression for K equals kappa KB T over H times the exponential of. And so now you can do experiments where you measure the rate constant, and if you know what these constants are, it's trivial to figure out, and you know what the temperature is, it's trivial to figure out what the change in free energy for the step you're interested in is. Okay, yeah?
Could you go over again what the difference between the three Ks are?
Okay. Okay. That was only funny to me. Here is K, the rate constant. All right. And that's the same down here and here. I didn't write this textbook, by the way. K double dagger is the rate constant for conversion of the activated complex into product, and it's derived from the frequency of a molecular vibration multiplied by some percentage of molecular vibrations that result in product. That's the other K, or kappa. Let's see, I've got 3 different colors. Now we'll go pink. Big K double dagger is the equilibrium constant for conversion of starting material into activated complex. And the rearrangement I sort of did in my head but didn't show you is if you want to substitute out the concentration of the activated complex, which we don't know, you can do it this way. Activated complex equals big K times concentration of A times concentration of B. And then we said that overall, combining this expression for K and then the definition here, we're going to put this in for activated complex, and that gives us this rate expression where big K double dagger times little k double dagger is equal to our original rate constant. I am sorry, I'm confusing myself. Okay, so I think we have 5 different K's because we have your friend and mine, the Boltzmann constant. All right, so by the time we get to the end of things, K, rate constant, kappa, transmission coefficient for how many times the vibration puts you over the edge, Boltzmann's constant, and that's it, because we substituted out the expression for big K. All right. Other questions? So you can rearrange this to find an expression for delta G, double dagger over the transition state. And this can be used even for multi-step reactions. This can be used for each individual step. All right. Now, before Eyring came up with transition state theory, there was already a theory of reaction rates from Arrhenius. I don't know how to, Arrhenius, I think is how you spell it, which may be more familiar to you. That is rate constant equals some pre-exponential factor times E raised to the minus activation energy over RT. And the difference is that Arrhenius's equation was empirical, and it was for the overall process, and there is not necessarily a clear connection between activation energy and free energy, unless the circumstances are sort of limited. All right. So this gives us a sense for the kinds of things that are involved in transition state theory. I want to show you a couple of things you can do with this definition to actually do interesting kinetic experiments. So suppose you have a process that you're interested in and you want to know whether the activation energy, you want to know how the activation energy shapes out between enthalpy and entropy, right? You can substitute this expression for delta G into the equation here. Before we do that, because sometimes we don't like to deal with exponentials, it can be easier to just take the natural log of both sides. And then this will just be delta G over RT. And then we can rearrange some things. We can subtract this natural logarithm for both sides, and subtracting logs is the same thing as dividing what's inside the log. So hopefully without a huge amount of persuasion, I can get you to believe that this is true. And then if we split that delta G up into minus enthalpy over R times 1 over T, and you've got minus T delta S over RT. The T's cancel, so I'm just going to erase them and move that delta S over. And if you measure K, if you measure the rate constant, which you can do in a kinetic experiment, and you do it as a function of temperature, and then if you plot the log of rate constant with all that stuff in there versus 1 over T, your slope is your enthalpy term, and your intercept is, and I'm sorry, that should be plus, your intercept is delta S over R. So that's more useful in the past than it is today. Computers today can regularly do fits of data with exponential expressions in them, but in the past it was a lot easier to try to get linear plots when you could, because linear regression you can actually do by hand without a lot of trouble. So let me show you the kind of experiment where you measure the rate as a function of temperature and then plot it. That is still today called an Eyring plot. So I get a little giggle to myself every time I see the words Eyring plot, because that comes from Mormon chemist Henry Eyring. Let me show you an example of an Eyring plot. So this is the Eyring plot for the breaking of a cobalt. This is the Eyring plot for the breaking of a cobalt carbon bond in vitamin B12 by an enzyme called ribonuclease triphosphate reductase as a function of temperature. So to get you oriented a little bit here, on the x-axis is 1 over T. So larger numbers means lower temperature, which is kind of confusing. Higher temperature to lower temperature. Okay, and then on this axis you basically have the natural log of rate divided by temperature. And I think for this reaction they're assuming that kappa equals 1, which is why you don't see kappa in that expression. So if you look at this plot, it looks like there's two distinct linear domains here. You've got, you start out at higher temperature, and as you lower the temperature, and remember the body's temperature is around 37 C, so you're going from sort of regular temperatures that this enzyme might see. You get below 32 degrees, and it's almost like you see the slope change. Okay? So remember, slope equals the opposite of enthalpy over R. So let's talk about, purple domain and, I don't know, orange domain. Okay, so in the purple domain, that slope is positive or negative? Negative, right? Sloping downward to the right is negative. So if you have a negative slope, what does that mean for what your enthalpy value is? Yep, enthalpy, activation enthalpy is greater than 0. All right. Similarly, in the orange domain, we see that we have a negative slope, and that tells us that activation enthalpy is also greater than 0. Now, what about the relative enthalpies before and after 32 degrees? What changes, and in which direction does it change? Think about magnitude of the slope. In orange, negative slope and its magnitude increases. Slope gets more negative, which means delta H gets even more positive. So that we would say that the enthalpy for the orange section of our plot activation enthalpy has got to be higher than in the purple section of our plot. Now, go back and remember the relationship between delta G and enthalpy. What does that say about your energy of reaction and therefore your reaction rate? Slower, right? The reaction slows down below 32 degrees. And so that often represents a change in mechanism or a change in what the rate determining step is. And that can be informative. In this case, the researchers found that below 30 degrees, the enzyme went through a conformational change that converted it into a less active form. And above 32 degrees, it was in a more active form. And the reason the enthalpy of activation goes up is because once the enzyme is already in the less active form, before it can do the catalysis, it's got to change its folding to get into the active form, and then it can go, right? So we've just tacked on some additional geometry changes and therefore enthalpy changes that we have to do in order to get to the active form that can do the reaction. We could talk about entropy as well. The intercepts where 1 over T equals 0 and temperature equals infinity, I guess, is what delta tells you delta S over R. Go ahead, Jared.
This graph kind of makes it seem like the rate of reaction will change suddenly at one temperature to the next.
Yeah.
Not a gradual change.
It can be a gradual change, and if the Eyring plot is curved, that can mean that the mechanism is complicated, more complicated than you thought. If there's an abrupt change, it often reflects a change that you can do experiments about, like a single change. And in this case, they tracked it down to, oh, it's probably enzyme shape.
So is this fairly typical where the reaction rate will be constant until a certain temperature or it changes suddenly?
Well, the reaction rate is not constant. It varies with temperature, but it does so in a way that depends on delta H and delta S. Because if you go back to what we're measuring here, you can measure the rate constant, but what we're plotting is the rate constant divided by temperature. And then temperature can affect also this delta G value. Dakota, you had your hand up.
Yeah, the rate doesn't change suddenly. It's slow. The rate averages the natural log of rate.
That's right. Yeah, I mean, it's what we're looking at is natural log of rate. So you're right. If we were actually plotting just rate constant, the plot would look different. You can ask a question, though, just from a qualitative point of view, why does increasing temperature tend to speed up reaction rates? And what we would observe from our plot here is that as you increase temperature, at least in this case, and the mechanism changes, the enthalpy gets more favorable. But why does the rate change in this linear region? Right? What's going on there? And the basic reason that the rate changes in that linear region is because as you increase temperature, you're increasing the kinetic energy. There it is. You're increasing the kinetic energy available to molecules on that potential energy surface. So here you've got two different temperatures. On the y-axis, you're seeing the probability distribution of kinetic energy at a certain temperature. Temperature 1 is lower than temperature 2, so as we increase the temperature, we switch the population of molecules from having average kinetic energy in this part of our graph. I'm sorry, I'm struggling here. Why won't it let me point to the graph? All right. The average kinetic energy in this portion increases as we increase temperature. And if we have some activation energy barrier, more molecules have enough energy to go over that barrier. And so the reason the rate changes with temperature for a simple one-step process is just you turn up the temperature, the molecules have more kinetic energy to get over the transition state. All right, there's some technical things in your book that talk about why it's okay to assume an equilibrium between the transition state and the starting material, even though that's really not the case. It has to do with the fact that saddle, just a second, Dakota, that saddle can be traversed by multiple pathways, and the further away you are from the lowest energy point over that saddle, the less likely it is that you're going to be there. So overall, if you were to watch particles go over this transition state, you would get a distribution of trajectories somewhere like this, where most of them pass pretty close here, and then some of them pass here and here. And that idea is the connection between statistical mechanics and that equilibrium constant expression that Eyring used. That's a technical point that I don't really understand myself, so we won't worry about it. Dakota.
Yeah. Having an equilibrium between the starting material and transition state doesn't really bother me. If you think about it, if we were to imagine an intermediate with the same energy as the transition state, it wouldn't be the same.
Yeah, I suppose if you were to imagine an intermediate with the same energy as the transition state, could you do a similar equilibrium? Yeah, I haven't thought through all of the implications on that. Let's see. Oh, you can do this sometimes in a comparative way. And your book talks about this. I'm just going to show you some of the data. So there's a reaction a photochemical reaction where you start with the phenanthrene precursor here, molecule I. You use UV light, and you can cause this carbon connected to the chlorine and the benzyl group to pop off as a carbene, leaving this stable aromatic phenanthrene system behind. And then that carbene can do two different things. It could recombine at some rate, K sub R, to give you an alkene, or it could insert itself or add to a different olefin that you provide. So A is for addition, Ka. And and I'm not sure technically how this was done, but they measured the rate of appearance of both products, and then they plotted the ratio of those rate constants, the log of the ratio of those rate constants against each other, and then they did that versus 1 over T. And they were able to determine, looking at that slope, what that slope tells you. Now the slope is positive, and remember that our slope is going to be related to minus delta H over R. If we're doing this as a comparison between two types of reactions, the slope is actually going to represent, and you can do math to show that this is the case, that this is now the difference in activation enthalpy between the two processes. So let's think it out. The slope here is positive. That means delta delta H double dagger should be what? Look at my definition here. I feel like I've lost everybody, so let me take a step back. Questions?
Sorry, why are there two deltas in front of each?
All right, I went through this, I think, let me, if I can, I'll answer that question. It'll take too long to write it out, so I'm going to show you something I was writing for myself to try to understand this stuff. All right. so, nope, just this. All right, so supposing I had two reactions, reactions 1 and 2. I could write an equation for reaction 1, K1 over T times some constants, which I'm not going to write out, and that would equal minus delta H for that reaction 1 plus delta S over R for that reaction 1. And so that's the first reaction. I could do the same for a second reaction, reaction 2. Constants here. Delta H for reaction 2. And now I'm going to subtract these two equations. All right? So on the left-hand side, we have the natural log here of rate 1 times constants, rate 1 over t times constants, natural log of rate constant 2 over t times constants. And then on the right-hand side, we have all of the r and 1 over t stuff remains the same. We're subtracting, though, delta H2 from delta H1. So that's where our delta delta H is, and similarly with our delta delta S. And if you combine these logarithms, the constants and even the temperature all cancel each other out. So if you plot the ratio of rate constant for process 1 versus process 2, the slope of that's going to tell you about the difference in activation enthalpy between those two processes. So if we look at the graph I was showing you, slope is minus difference in activation enthalpy. The slope is positive. That means delta delta H double dagger is negative, which would mean that Ka, the process Ka, has a lower activation energy than Kr. And your text did the math and says it's about a 1.6 kcal per mole difference in activation enthalpy for the faster process relative to the slower one. So in this case, we conclude that I think the addition is the fast one, and it's faster because of lower activation enthalpy. And that's interesting because you can attribute activation enthalpy to, say, favorable interactions in the transition state or stronger bonds forming in the transition state. And so you can get an idea, a better idea of what the mechanism is. All right, so that's it. This stupid collar is killing my neck, and I am sweating inside here, and we're all overwhelmed and bored with kinetics. So we're going to pause today, and we'll pick this up again next Friday. Until then, have a happy Halloween.